Here are the slide chunks broken up by theme. The amount of sunlight that strikes Earth in just 90 minutes carries enough energy to power every city, factory, and home on the planet for an entire year. Capturing even a tiny fraction of that energy has been a scientific obsession since 1839, when French physicist Edmond Becquerel noticed that certain materials produce small sparks of electricity when exposed to light. He had stumbled onto the photovoltaic effect, a phenomenon in which photons transfer their energy to electrons inside a semiconductor, knocking them free and setting them in motion. That motion is electricity. Today, the most common semiconductor used in solar cells is silicon, and the underlying physics has not changed, though the engineering has become remarkably sophisticated. A modern photovoltaic cell is built from 2 layers of silicon that have been deliberately doped with impurities to create opposing electrical charges. One layer carries extra electrons, called N-type, while the other has gaps, called holes, where electrons are missing, known as P-type. Where these 2 layers meet, an electric field forms at the P-N junction, which acts like a one-way gate for electrons. When sunlight hits the cell and energizes an electron, that built-in field pushes the freed charge carrier toward conductive metal contacts on the cell's surface, producing direct current electricity. An inverter then converts that direct current into the alternating current that homes and businesses use. The elegance of the system lies in its simplicity. No moving parts, no combustion, and no emissions during operation. Not all silicon solar panels are created equal, and the distinction begins at the molecular level. Monocrystalline panels are manufactured using the Czochralski method, in which a seed crystal is slowly drawn from a vat of molten silicon to form a single, continuous cylindrical ingot. That ingot is then sliced into ultra-thin wafers. Because the crystal lattice is perfectly uniform, electrons encounter fewer obstacles as they flow through the material, which translates directly into higher conversion efficiency. Top monocrystalline panels now routinely exceed 22% efficiency, with the best commercially available models pushing past 25%. They also tend to last longer than other types, with performance warranties stretching to 30 years. Today, monocrystalline technology accounts for approximately 98% of all solar cells produced globally, a dominance that reflects both its superior performance and steadily declining manufacturing costs. Polycrystalline panels, once a popular budget alternative, have largely become a legacy product. Rather than growing a single crystal, polycrystalline manufacturing melts silicon fragments together, producing a wafer composed of many small crystal grains. Those grain boundaries impede electron flow and reduce efficiency, typically capping out several percentage points below monocrystalline performance. Major manufacturers have phased out new polycrystalline production lines in favor of higher efficiency monocrystalline technology. For anyone planning a new solar project, the choice is effectively settled. Monocrystalline silicon delivers the best combination of efficiency, longevity, and value per kilowatt-hour generated over the system's lifetime. Traditional silicon panels are rigid, heavy, and limited to flat or gently sloped surfaces. Thin-film solar panels solve that problem by depositing a microscopically thin layer of photovoltaic material onto a flexible substrate such as glass, plastic, or metal. The result is a panel that can bend, wrap around curved surfaces, and weigh a fraction of its crystalline counterpart. 3 primary materials dominate thin-film production. Cadmium telluride, which is the second most common photovoltaic material after silicon. Copper indium gallium selenide, which offers high lab efficiencies but is complex to manufacture. And amorphous silicon, a non-crystalline form of the element. Thin-film panels generally achieve efficiency ratings between 7% and 13%, substantially lower than monocrystalline options. What thin-film technology sacrifices in peak efficiency, it gains in adaptability. These panels have been tested aboard spacecraft, integrated into military field equipment, and installed on recreation vehicles and portable shelters. The energy payback period for thin-film panels is among the shortest in the industry. meaning they repay the energy used to manufacture them faster than most silicon panels. On the frontier of thin film innovation, researchers are exploring solar fabrics that could be woven into jackets and backpacks. In 2025, a concept laptop was unveiled featuring 84 ultra-efficient solar cells built directly into the device, achieving over 24% conversion efficiency. These developments point toward a future where photovoltaic material is embedded into the surfaces of everyday objects, quietly generating power from ambient light. The most exciting chapter in solar science is being written by a mineral first discovered in Russia's Ural Mountains in 1839. Perovskite is a crystalline material that can absorb a broad range of light wavelengths, is cheap to produce, and can be printed, coated, or deposited onto substrates at low temperatures. When a layer of perovskite is paired with a layer of conventional silicon, the result is a tandem cell that captures energy from portions of the solar spectrum that either material alone would waste. Silicon excels at absorbing red and infrared light, while perovskite handles the blue and ultraviolet end. Together, they shatter the theoretical efficiency ceiling of approximately 32% that limits any single junction silicon cell. In April 2025, LONGi achieved a certified tandem efficiency of 34.85%, verified by the National Renewable Energy Laboratory, and has since communicated results approaching 35%. The progress has been stunningly rapid. Perovskite cells managed only 3.8% efficiency when first demonstrated in 2009. Jinko Solar reached 34.76% on TOPCon-based tandems, and researchers published a flexible perovskite silicon tandem cell, achieving 33.6% efficiency while surviving 5,000 bending cycles. Commercialization is already underway. Oxford PV shipped 24.5% efficiency tandem modules to utility customers in 2024, and Hanwha Qcells plans mass production of tandem panels in 2027. The primary challenge that remains is durability. Perovskite degrades when exposed to moisture, ultraviolet radiation, and sustained heat, so scientists are developing advanced encapsulation techniques and more stable chemical formulations. Japan has committed $1.5 billion to commercialize perovskite technology, signaling global confidence that these stability hurdles are solvable. Bifacial solar panels capture sunlight on both their front and rear surfaces, harvesting reflected light that bounces off the ground, snow, water, or pale-colored rooftops. Depending on the installation environment, bifacial modules can generate 5% to 30% more electricity than conventional single-sided panels. They are typically built with dual glass encapsulation, making them more resistant to hail, UV degradation, and temperature cycling. Floating solar farms, an emerging category sometimes called photovoltaics, mount bifacial panels on bodies of water. They simultaneously generate clean energy while reducing reservoir evaporation and limiting algae growth. Solar tracking systems add another layer of optimization by tilting panels throughout the day to follow the sun's arc across the sky. Single-axis trackers rotate east to west and can boost energy output by 15% to 25%, while dual-axis systems adjust both horizontally and vertically, increasing yields by as much as 30% to 45% in optimal locations. The latest generation of trackers incorporates artificial intelligence that learns site-specific weather patterns and adjusts positioning in real time rather than following a fixed schedule. Paired with battery storage, which grew to 26 gigawatts of grid-scale capacity in the United States by 2024, these systems make solar power available even after the sun sets. Installed solar capacity is projected to double from roughly 2.9 terawatts in 2025 to over 6 terawatts by 2029. Whether on a single rooftop or a floating array, solar technology is rapidly becoming not just an alternative energy source, but the foundation of the modern electrical grid. Thanks for watching. If you have anything to add, drop a comment below. Don't forget to like and subscribe for more videos exploring the world around us.